Awesome. Hey, everybody. Welcome to my very spicy talk called Can My Neighbors Figure Out What Fanfic I Read Online? So, what this talk is actually about is HTTPS and kind of like a little bit of a history of it, and also a realistic view of what it actually does for you as like an individual who uses the internet. So first I'm gonna start with the history part. Okay, so imagine this is probably hard for most of us because we were born after 1995. Um, but OJ Simpson, he's in court, all that good stuff. eBay just started. Everyone's starting to realize the internet is a pretty cool thing. Okay, they're surfing the web. People have got computers. They definitely don't have laptops. This image is a little misleading, but uh, people are starting to get computers. They're getting connected to the internet, and people are using the first browsers basically to browse the internet. And so let's say in 1995, I want to connect to my favorite website, okay, and I want to get the homepage or something, or my favorite fan fiction, for instance, okay. So what my computer would do is, I mean, it'd be connected to dial-up or some ancient technology, but whatever communication method, it uses the HTTP protocol, which is basically tells between the computers how to but on the internet, right? So like you can have get or post, or there's different requests for resources basically on servers. So like this is an example one, for instance, and then the server would respond with the actual resource that I wanted. So in this case, that would be the website, right? And so if I wanted to go to eBay, for instance, since this company was just starting up and they're starting to realize all these different technical challenges, right? So if I make a connection to eBay on my Netscape browser, okay, and I try to buy something with my credit card, then my credit card number has to be encoded in there somewhere, right? And that's a problem for HTTP because HTTP is sent over the network in plain text. And what that means is that anyone who sees your packets in flight, so like the person who controls your router, or the person who controls your internet service, or the person who controls any of eBay's routers or internet service, can see that data in transit. And so if there's someone malicious in the middle, then that attacker can read your data, steal your credit card. And so this was a huge problem for companies back in the day. And so Netscape basically came up with a whole new protocol to get around this problem. And so basically what they used was previous protocols. Basically, like there was existing protocols like TLS, which basically give you an encrypted connection. And the way that works is that two people who want to communicate share their keys or their public keys, and then they can use RSA or like a public crypto system to get a symmetric key basically, and then encrypt their information between them. And so like they have to do this handshake first where they exchange keys, and then now when they send data back and forth, it'll be encrypted. And so Netscape developed this for HTTP back in the day when they were trying to facilitate online transactions and stuff like that. And so they initially called it something that wasn't HTTPS, and there were competitors like SHTTP and a whole different naming scheme back in the day, but eventually it just became called HTTPS. And the whole idea behind HTTPS is that we use this two-way handshake, the three-way handshake, to encrypt the traffic between two people who want to talk to each other. And so that way, attackers in the middle can't, for example, like look at your login information when you log into a website, or they can't read your credit card numbers because they're encrypted now. And now they can't tell which things you're looking at on a site, right? Like if you request like a specific fan fiction story, okay, then the attacker has no idea which one you're requesting because all these things are encrypted now. So that seems like it was a long time ago, and we don't have to worry about that anymore because we all use HTTPS now, right? But all that Snowden stuff back in the day, there was crazy controversy about the government spying on you and all this stuff. But almost all companies only used HTTPS for login and payment pages until very recently. Like Amazon famously held out using HTTP on their main website for like a super long time. And this graph shows you like how much of the actual web traffic is encrypted with HTTPS over time. So there wasn't even that much data before 2014. I couldn't really find any data before 2014 because so few people were used HTTPS. And even back in 2014, only like 30% of people or 30% of web traffic was loaded using HTTPS. And so even though it seems super long ago that we even had this concern, it was really recently that people could just straight up view your traffic in plain text and just see, oh, you're logging in with this password, I can just use this password. And even the companies that were using HTTPS for login or payment pages, attackers could still see exactly what you're doing on the internet for things that weren't those pages, right? Like if you go to a specific Facebook page, any network attacker can see what you're doing. So for example, like the government or any internet service provider could just collect all this information for free. But luckily now, as you can see, like almost 100% of traffic is loaded with HTTPS, around like 85% right now. And so we might think like now that we're using HTTPS, we can just do whatever we want, right? Like we can log in, no worries about anybody stealing our credentials. We can use credit cards on the internet because we know it'll be encrypted. So you might think that we're completely safe to just do whatever we want, but not exactly. So nowadays, if we actually communicate between a server, right, we have to send a packet. And the packets I've been showing you right now are just the very high level, higher level in the networking stack, right? So you send an HTTP packet, an HTTPS packet, which is on top of an IP layer packet. So basically, your HTTP packet needs to know where to go, right? So it has to be able to communicate with other intermediaries in the network without, like, the router, for example, doesn't know the key that you shared with your bank and your computer, between your bank and your computer, right? And so the router can't decrypt your whole packet. So HTTPS has to piggyback on unencrypted protocols, right? So like the IP protocol, for instance, it has a source and destination header. So now your router can tell where the packet needs to go because obviously it needs to know so that it can route it to the next destination to ultimately get it to where it wants to go. But you also have other fields like the size of the packet, which just basically tells your router, okay, this is when my packet is going to end based on how long I say this packet is going to be. And then there's even lower level payloads like your MAC layer payload, which says like, this is my MAC address, and this is the 14,000th packet that I've sent in this sequence. And so there's all this extra information that kind of goes on under the hood that we don't think about. And so now the attacker can tell you're going to bank.com, for instance. And so the IP, like the IP layer source and destination headers, just tell any network attacker that you're basically just broadcasting who you're communicating with. And so you might think, I mean, that's okay. Like, I don't really care if they find out I'm going to X site or something like that. But it's even worse than that, because if the attacker sees a bunch of different packets, right, they can also look at the size of those packets. And the size tells you something as well, right? So if I send a packet that's 258 bytes or something like that, then I as an attacker can go to the site that I know you're looking at. And now that I know you're on this site, I can go looking for things that are 258 bytes. And so like if I request this image, for instance, it might be exactly 258 bytes. And so when I see that you just got a packet that's 258 bytes, now I know you're probably on the login page because you just got a resource that was exactly this size. Because, I mean, it's possible that there's some other resource on the site that's 258 bytes, right? But knowing that the packet is 258 bytes narrows down the options quite a bit. And so you can imagine if you load a bunch of these different resources, the attacker can basically use like a statistical attack against you and say, based on the sizes of the packets they've sent, now I can guess which pages they're on as well. And so this is kind of a bad conclusion for HTTPS, right? Even though all our traffic is encrypted, adversaries can still guess what you're browsing through your browser. And it turns out this is actually a really old idea. The first paper that I found to actually talk about this idea was from 2002, before basically anyone was using HTTPS. And so this is like a little diagram that they came up with to explain basically what I'm going to talk about for the rest of the talk. And so before I get into the actual idea of the attack and how you would actually do this attack, I just have to put a disclaimer here that you can't actually, or there has been precedent of like people sniffing other people's network traffic, and that's definitely illegal unless you own the network and you have their consent. So you can basically only do this to yourself or like someone that can explicitly tell you that it's okay to collect their traffic. But what I'm going to talk about next is basically how could we exploit the facts that I've just talked about to actually guess someone's browsing history. So for the purpose of this talk, I'm going to talk only about Wikipedia. So basically someone's browsing on Wikipedia and we're going to try to guess which pages they're on. So for what we're going to do as an attacker is just load a bunch of different pages on Wikipedia. And then when we load them, we keep track of the sizes of the packets that get sent back and forth. So for example, if we load the page for Facebook, for instance, we might get a logo of Facebook or something. And that will have a specific size, right? Just because the image is very large, so you're going to have a big resource to load, and it's going to be compressed, so it's going to have a semi-random size. And so that ends up meaning that you'll have a lot of small requests that are basically just like, get this resource. And so then it's hard to unentangle, okay, which site is this? But you'll have a lot of really large resources that are images that will give you a lot of information about which actual resource you're loading. And so like if you saw as an attacker that someone loaded a resource that was 12,400 bytes, then all of a sudden you know, oh, they have to be browsing the Facebook page on Wikipedia. And then the next thing that you do as an attacker is you just sniff someone's traffic, right? And you do exactly what we were talking about before. So first you figure out, okay, they're loading something from wikimedia.org. And the size, if we look back at our chart, corresponds to a specific page that we saw. So like, for instance, here we saw 8,500 bytes. So now we know they're browsing the Wikipedia page for the US. And then now as an attacker, just with this prior knowledge, we can figure out exactly what you were doing on your browser. And so I actually implemented like a proof of concept for this, where the victim basically just like randomly browses to one of the top Wikipedia pages, and then the adversary just tries to predict which page the victim was on. And so in this instance, the attacker is a wired attacker, which means like they control your router or your ISP or something, someone who has access directly to the packets that you're routing. And so if we, on the left here basically tells you the data set I'm using. So like if the victim is browsing within the top 10 sites, then it's just a random Wikipedia page among the top 10 most popular Wikipedia sites. And then here's the middle column is accuracy. So how well did the attacker guess which page they were on? And then the third column is accuracy top 5, which just means if the attacker gets 5 guesses, can they get it right? So if you just look at the top 10 sites, then in this case, my like simple proof of concept was basically able to figure out 86% of the time exactly which site they were on. And if you give the top 5 guesses, then it's really easy, obviously. So you get 100%. And then as you get more and more possible resources that the victim could be loading, the problem gets a little harder, right? And so the attacker does a little more poorly, but it's still a lot better than average. And even when you go to like 100 sites, the attacker still has a 75% chance of guessing it within the first 5 guesses, which is way better than random guessing, right? And so I also did this for like a wireless environment. So like if you were browsing on like a free Wi-Fi network or something, then attackers can basically just sniff the packets that are going through the air, right, through Wi-Fi. And based on that, they can figure out which sites are loading. And so in this example, like I had a victim who was browsing like 20 meters across a building from the attacker. And even then, in these different wireless configurations, the attacker can still guess with really high accuracy what the victim is doing. And then there are also some funny mispredictions that the model came up with. So one was like, if the victim browsed the UK, then the model would predict World War I. If the victim browsed presidents of the US, it would predict Abraham Lincoln, which kind of makes sense. But if you browse Elon Musk, the model thought you were looking at the Illuminati. So I'm not sure what that means, but. And then if you browse the Illuminati, it predicts Justin Bieber. So I think the model is smarter than us at this point. But beyond just like this proof of concept, what does this actually mean for us as people who use the internet, right? I mean, I feel like my intuition to this would be like, who would actually do this attack on me, right? Like if I'm just at Starbucks, no one cares what I'm browsing, right? Like if I find out the guy next to me is on r/stocks or something, or he's buying GameStop on Robinhood, like who cares? But this whole process, like I described, could be completely automated. So like you don't need like someone individually, like your FBI agent, to just like spy on you and figure out what you're browsing. You could do this all automatically just with like a couple programmers basically. And then this all information is also kind of useful to people, right? Like that's why Google basically makes money off of tracking your browsing history, right? And so they do that through a different process, but your ISPs could also be doing that, right? Like any of your cell carriers or the people who actually provides internet in your house, like they could be doing this kind of analysis and just sell that information to advertisers. And it's completely legal as well. And the government can also do this, like basically with no, like using loopholes basically that were passed after 9/11, like the Patriot Act. The government can actually just do this like without getting a court martial or a warrant or anything like that. And so if you were doing this in like a free network or something like that, then your connection is unencrypted. So like I was saying, like attackers who are just in the area can spy on you and read your traffic. And so now we probably need to ask, like, how can we prevent people from doing this? Like, is there anything I can do as someone who uses the internet to avoid this? And so one thing you can do is just don't use free Wi-Fi networks, right? Like if you're using a free Wi-Fi network, just be aware that anyone can sniff your traffic through the air, and they can see which sites you're browsing to and which resources you're loading. And if you're not comfortable with that, then you should use a Wi-Fi network with that's password protected. And as like a more general approach, you might think like there are a couple things we could do, like just like have your browser just randomly request things to try to confuse the attacker, or like change the size of packets randomly so that they're like a constant size or something like that. But basically, like statistical attacks can get around all these kind of random changes. And especially as like a user of the internet, like you can't make these changes to the networking stack, right? So as someone who just uses the internet, if you want to avoid having this problem, then you can use a proxy server basically. And so what that does is just you encrypt your connection to the proxy server, and then anybody who looks on your traffic in between just sees you're talking to a proxy server, and they have no idea what like website you're connecting to or anything like that. And even though there are some attacks that are like that can be pulled off in theory, that are like ways to match you to the proxy server, and then if you have like some super Illuminati type thing, then your ISP could theoretically like spy on the proxy server and you, and then match the two and figure it out. But assuming that like the proxy server is using a different internet service provider than you, then this is almost always safe. And so if you want to learn more about this attack, I've linked a couple papers here and also some of my code. If you want to like try this out, you can actually run it like on Macs. I think it should work. You can actually use like there's a built-in Mac utility to like sniff wireless traffic. That's pretty cool. And so you can use that in conjunction with my code to actually like pull off this attack if you want to on yourself, if you have consent. But besides that, that's it. Does anybody have any questions?